All right. Hello, everybody. This is going to be kind of a Unit 2 crash course, more or less, in correlation for AP statistics. So I'm going to go as quick as I can and kind of hit the high points, give you some definitions, and then we'll show you some examples on how to do some of this stuff. So here we go. Just to be clear, the topics I'm covering, this is the stuff that is set forth by the College Board. These are the things included in Unit 2. We're going to pick up right here at 2.5, we're going to start with correlation. So we're going to start with correlation, and then we're going to work our way down all the way to the end of analyzing departures from linearity. So these are the parts that we're going to cover. If I'm being honest with you, 2.4, 2.3, this kind of starts to get into like, especially 2.4. 2.4 is kind of Unit 4 type stuff because we're going to revisit this and talk about probability whenever you're talking about two-way tables and contingency tables and that stuff. So we're going to go back to that, but that'll be something else. So first, we're going to start off with correlation. Correlation, to put it simply, is the measurement of direction and strength of a linear relationship between two quantitative variables. The two quantitative variables, of course, is very important here. You cannot do correlation or regression, as it's called, if you have categorical variables. It only works with quantitative. So here's some general facts about correlation. First, it's always between -1 and +1. It's a number. It's going to be a decimal. Usually 3 or 4 decimal places will be fine for an R value. R itself has no units, and it doesn't care which one's explanatory and which one's response. So if you accidentally screw up which one's X and which one's Y, your R value will be the same. The rest of what we are going to do will be different, but R at least will be the same. Correlation does not equal causation. What this means is, and you can look online, there's all kinds of funny scatter plots out there. Nicolas Cage somehow has a correlation. The movies that he appears in, the number of movies he appears in from year to year, has a correlation with the number of people drowning in swimming pools. That does not mean that Nicolas Cage is drowning people in swimming pools. What this means is there's some kind of coincidental relationship there. So there is, in fact, a correlation with these two things, but that doesn't mean Nicolas Cage is causing this stuff to happen. So correlation is not causation. They are not the same thing. The last two, R is for linear relationships only. That kind of needs to be said, but also what else is kind of interesting is that you only analyze linear relationships in the AP statistics course. So whether you care or not, I guess, is another matter entirely. But linear relationships is all we're able to talk about in terms of R. R is a lot like the mean. Uh, Without getting too far into it, the R is calculated based on the regression line is the means. So it's pulled easily by outliers. So if you have a very influential point or high leverage point, they're going to be easily affected by outliers. So your R value is not resistant, as it's called. So that's it for 2.5. 2.6 is the linear regression models. So this is where we get our official definition of the least squares regression line, which I boil it down to simply the line of best fit. The line of best fit is basically the line that goes through the middle of the scatter plot. It's the line that gets the closest-ish to all of the data and approximating all the data. The predicted value is also known as y hat. That's how this is pronounced, y hat. The predicted value for the response variable, and of course our response variable is y. That's why I wrote a y there. If you take some specific explanatory value for the explanatory variable and you plug it into the least squares regression line, it's going to spit out some predicted y value. And that predicted y value is what you are supposed to see given some specific value for the explanatory. We'll do examples of that. The slope is pretty much exactly what we know from Algebra 1 and Algebra 2. It's the slope of the line, which you'll see it as y equals mx plus b. M is the slope. We're used to seeing that. There's other ways that it's written too, so I'll show you those. The y-intercept is the exact same thing, but it's the predicted value specifically when x is 0. Because of this little multiplication here, m times x, well, if x is 0, this whole thing is 0, so you're just left with the y-intercept. Therefore, when anytime x is 0, you have the y-intercept that's left over. So I said that there's more than one version. Generally, okay, generally, we like seeing this version because it's familiar to us. We know about y equals mx plus b. We'll probably be able to tell you that equation until we die, when we're out of school for 50 years, 70 years, whatever. And we know that m is the slope and b is the y-intercept. We've known that for years. Well, there's this other version. Sometimes you see this, and it's the exact same thing. Don't freak out, because b times x, that means b is the slope, right? B is the slope because it's attached to x with multiplication. And same thing, if if x were to become 0, we'd be left over with a as our y-intercept. That's it. That's the entirety of the formulas, the functions, right? The least square regression lines. We're given these sentence frames when we go to actually interpret slope and y-intercept and all that stuff. So if we are to interpret the slope, this is the sentence frame that we use. We say for every one, and then we're talking about whatever units it is for the x variable. So I'll just put x var. So this is x var in context. So if we were talking about for every 1/2 shoe size, for every one shoe size you increase, the predicted, and then this is your y variable. So y var, the predicted, and what if this was height? So for every one shoe size you increase, the predicted y variable, so the predicted overall height, will either increase or decrease by, and then you put in the actual value for the slope. Value slope. So whatever b was, or sorry, whatever m was, so this is either m or b, depending on which formula you like to look at in the previous slide. So the value for the slope is what goes here. And then this is context. Obviously, if this number over here is positive, then you're talking about an increase. If this slope is negative, you're talking about a decrease. Hopefully that's pretty obvious. To interpret y-intercept, we say when, and then whatever it is we're talking about. In this case, whatever the x variable is. So if it's shoe size. When the shoe size has a value of 0, the predicted height, or y variable, predicted height, is approximately, and then you just fill in the value for the y-intercept, whatever that is. So this is the y-intercept, which is either a or b, depending on which formula you're looking at on the previous page. So make sure not to confuse this b and this b, because they are not the same. So know which one you're using and stick with that. All right, so that's how you interpret a slope or a y-intercept. 2.7, residuals. The residual, think of it like this. If we had, here's just some random scatter plot that I'm just completely making up off the top of my head, and then drawing a crappy line of best fit. So if we draw this line of best fit, and then I'll switch to blue, I want you to consider how far away from the line of best fit this data point is. So this data point vertically is whatever distance this is. This distance is the residual. That distance is the residual. So the residual is the vertical variation in the response variable. So draw a straight line, vertical straight line, from the data point either up to the line of best fit or straight down to the line of best fit. Because as you see up here, this data point is above the line of best fit, so you'd actually have to draw down in order to get there. So it's just the distance. That's all it is. The negative of the residual, so you can have negative residuals. If it is negative, that just shows that the data point was below what was predicted. We'll get into that. All right, the residual plot is a scatter plot of all the residuals plotted around the horizontal line of 0. So if this is a scatter plot, then the residual plot is centered at 0, and then usually they go down to like, I don't know, -8 and +8, and then there's some tick marks. It's all even. It's all evenly spaced. So if this right here, if we're looking at this data point is, say, 5 units below the line of best fit, then that data point, this data point right here, would be 5 data points below the line of best fit, or below 0. Right? So 0 would mean that the data point is directly on the line of best fit. So if the residual is 0, that data point's on the line of best fit. Hopefully that makes sense. All right, to calculate residuals, it's very simple. you're going to think AP statistics, which means you take the actual value. So let's say that a student actually had a height of 72 inches, but his predicted value based on his shoe size or his knee height was, I don't know, 68 inches. We expected him to be 68 inches tall based on his shoe size. However, his actual height was 72 inches. So you just do this subtraction, and then what your answer is, positive or negative, is your residual. You are allowed to have a negative residual. That shows that the person was below average or below the line of best fit. In this case, this person has a residual of 4, meaning that he is 4 units above what was predicted, which is the next thing we're going to do. And then the context, right? So this is usually the person, the thing. This is whatever the stats are about. So this is the subject. In my made up example, we're talking about the person that had a shoe size of whatever, doesn't matter. So X variable. The person with a particular shoe size that is, we just did the math, 4 units, or we're talking about his residuals, which doesn't really have units, so is 4 above what was predicted because his residual was a positive 4. So then you just put together this sentence and you're done. The last thing we'll talk about for residuals is the interpretation of the residual plot for a linear model. We'll get further into this in a second, but just to give you the sentence frame, due to either the presence of or lack of fanning or leftover curvature, the linear model is or is not appropriate. So you can say the presence of, and then either one of these. The presence of those things implies that it is not appropriate. If you do not have those things, the lack of fanning or leftover curvature means that the linear model is appropriate. So you're either going to pick presence and is not, or lack and is. So stick with those two. There's only 2 versions of this sentence that are going to happen. So let's look at some residual plots. So to be absolutely crystal clear, we should see randomness. We should not see fanning or leftover curvature. Basically, if there's any pattern in your residual plot, it's bad. So here's some good residuals. Here you have the average distances basically from all of the middle data points here, right? From 0. All of these data points were more or less clustered around the line of best fit. Some of them were further away than others. These are quite far away. But there's no pattern here. It really looks like someone took a fistful of SpaghettiOs and threw them at the wall. There is no pattern. Over here, it's the same thing. There's less data points, but it doesn't matter. They're all kind of randomly dispersed around this horizontal axis, which is 0. And if they're on 0, that means they're directly on the line of best fit. So some bad ones. This is what I'm talking about when I say fanning. As you can see, this kind of opens up as it gets further and further in the positive x direction. So as you go to the right, it fans outward. This means that as you go further down the line of best fit, the data becomes further and further away. They're actually missing the horizontal line here. This should be a line here at 0. As you're getting further down the x-axis, the data is getting further away from the line of best fit, making it a less than ideal model for that data. So this implies that the linear model is most likely wrong. Same thing here, except this is called leftover curvature. As you can see by this data, there's a slight curve in the data. That means that linear model is probably not the best fit. So at that point, you'd be testing and trying to find like what does fit. So maybe there is a quadratic model that fits. Maybe there's an exponential model that fits. All of that is outside the scope of this course. So just know if you see fanning, this is fanning, or you see curvature, those two things equal bad. So that means that the linear model is most likely not appropriate for this data. Okay, the last section is 2.8, least squares regression. We have this thing called the coefficient of determination, otherwise known as r squared. R squared is the proportion of variation in y that is explained by x. And you form your sentence frame just like that. I think that's on the next slide. The standard deviation of the residuals is the average prediction error. There's a big ugly formula that goes along with it. I won't force you to memorize it because it's on your AP formula sheet. Okay, some facts about the coefficient of determination. Again, this is r squared. It's a number between 0 and 1 because think about it. If you take r, which could be positive or negative, and you square it, it's forcing it to be positive. So r squared is always going to be greater than 0 or equal to 0 if you have an exactly 0 correlation. So it's always between 0 and 1, and it's expressed as a percentage. It's got no units and doesn't care which one's the explanatory versus response. Here's the sentence frames. To interpret r squared, we say fill in the blank percentage, so this is the actual value for r squared. The variation in the response variable, so in this case the y variable, and make sure to include context. Don't just say y variable, you're going to lose points on the AP exam, is explained by the x variable. So in my made-up example that I've been using, let's just make up an r value. How about 92%? 92% of the variation in height is explained by shoe size. Okay, so there's an example of that. To interpret the standard deviation of the residuals, we say that the typical prediction error is, and then usually this number is either calculated by formula, it is produced by your calculator, or it's given to you. It's very common to be just given to you, but whatever you fill in here, it's usually written as S of something. So it's like the standard deviation of the residuals. So look for an S either in your calculator or on a mini tab output, which we'll talk about that. And then this units is whatever units are on the response variable. So you fill in the number here. It's usually an S equals something, and then you fill in the y variable, context, units, all that stuff. Here are the two formulas. Again, these appear on your formula sheet, but if they just said, here's the standard deviation of both of these things and the r value. I've seen this before. They give you r, they give you the standard deviation of the y variable, the standard deviation of the x variable. You can calculate the slope if you're given those three things. Once you have the slope, you can take the slope and plug it in here, and they give you the mean of x and the mean of y. Now you can also calculate this, which would be the y-intercept. Obviously, in this particular example, they're using the y equals a plus bx version of the linear regression formula, and that's perfectly fine. So this is the version that you will see on the AP test. Again, for our purposes, if you'd rather use y equals mx plus b, I don't care. So just know that this is the one that you're going to see on the test, on the AP exam, I mean. So, all right, departures from linearity. This is very brief. An influential observation is an outlier that if you take it out, will drastically change the relationship or the R value between X and Y. A high leverage point is a point that still follows the overall pattern, but is like way bigger or way smaller in terms of X than the rest of the data. So a high leverage point is something that's like, if all of the data is in single digits and then you have an X value of like 40, that's a high leverage point. That's really far away from the rest of the data. Even if it follows the same pattern, it's considered a high leverage point because it's way out there. And that's that. So let's run through discard. Let's run through some examples of stuff. So what I've got here is this thing. So I've got this data pulled up, and then over here I've already typed it into Staplet. That you can use any graphing calculator you want. This, I find Staplet to be very simple. So you type in the data in order. That's very important, and then hit begin analysis. It'll give you the scatter plot. And oh, well, I guess I should go in order, right? So let's go in order. Draw. Make this small. All right, so the explanatory variable in this case, number of drinks. The response variable is the other one. This is blood alcohol concentration. Write the least squares regression line for this data and write it in context. So after you type in the data, you hit calculate correlation, calculate least squares regression line. So here is the data with the least squares regression line inputted. If you scroll down, it gives you the actual equation of the data, same as your calculator would. It's missing the context though. So to be very clear on the context, we're talking about predicting blood alcohol concentration as a function of the number of drinks that you have. So this is the 0.0024 plus 0.0287 times, and then I'm using words, number drinks. Okay, so this is your least squares regression line in context. Interpret the slope. This is going to be the sentence frame that we looked at earlier. This is for each or for every additional drink. So in this case, this is my x variable, this is my y variable. So interpret the slope. For every one drink, I guess we'll say one drink consumed. For every one drink consumed, the predicted blood alcohol concentration, BAC for short, increases because the slope is positive in my least squares regression line. Increase the blood alcohol predicted BAC increases by 0.0287. And I don't know the units on blood alcohol concentration, so I'm just going to leave it like that. All right, next is find the value for R. Well, it tells us. R is in fact right here. So we know R. This is 0.99. It told us. Interpret R. So interpreting R is talking about the relationship between X and Y. We have a sentence frame for that too. This is the relationship between, sorry, I'm kind of looking at my cheat sheet on the side. Relationship between the number of drinks and blood alcohol concentration is linear, positive, and strong. So I'm hitting the main points. They want to know whether or not it's positive and strong. I kind of threw in the word linear, even though you don't really need to, because again, R value has to be linear. Okay, find the value for R squared, which is simple. You take the R value and you square it, which they also give you down here in the output. So that is also, I kind of wrote over it. So this is 0.98 is the value for R squared, and 0.99 squared. Okay, interpreting R squared. Interpreting R squared, this is 98% of variation, I can't spell, variation in blood alcohol concentration is explained by number of drinks. Okay, there's that. What is the predicted BAC for a person of this weight when they drink 8 drinks? Show your work. Okay, so this means you take the least squares regression line, which, let's scroll up so I can see it. This is 0.0024 plus 0.0287 times x, which in this case they're telling me I'm predicting 8, so 8 goes right there. And then you go through the steps. You just use any calculator you want for that, and we're talking about predicting the blood alcohol concentration. And after some buttons on the calculator, you find it is 0.2318. So that is your answer there. On this next page, we're doing all kinds of different stuff. I'm actually going to skip number 15 because this is a very difficult question. I gave you the tools to do it. If you want to try it, you are welcome to, but it's not easy. It involves those formulas on that one of the last slides. So if you want to do it, you can. This thing here, this is a Minitab output or an SPSS output. It kind of depends on what software they use. So here we have the coefficients we get S, which is our standard deviation, and we get R squared. It tells us all this information here. So really, we're going to use these numbers in these boxes. We don't need anything else. We just need to know how to read these. So in this case, it looks like, if you read the question, believes that a son's height is closely related to their father's height. And then, okay, so our variable appears to be dad height. So dad height is going to be our explanatory variable. And then we're trying to predict son's height. So son's height is going to be y. So determine the least squares regression line. That's just a matter of pulling these numbers out of the output and putting them into a least squares regression line type format. So this is the thing we're trying to predict. So I'll put son for son's height. We're trying to predict son's height. And then we have a constant, which is 12.023. And we think that for every 0.84238 inches that the dad is tall, that will now affect the son's height. All right, so the correlation coefficient, this is easy. They gave us r squared. So in fact, all we have to do is take r squared and square root it. So you take 0.887, square root it, and it will give you r, which is 0.9418. So there's your correlation coefficient. The estimated height of a son whose father is 70 inches tall, which means we're taking this equation and plugging in a 70. So this is 12.023 plus 0.84238, plugging in 70, because that is dad's height. We're still trying to predict the son's height. And after some clicky on the calculator, we come up with 70.99, and then now I know the units, inches. We're talking about he's inches tall. All right, what percent of the variation in son's height can be explained by the father's height? That's easy. This is the sentence frame talking about r squared. So it's this percentage of the height. So this is r squared, which is that number there. They already gave us that. And then number 14, calculate the residual for a son who is 69 inches tall and has a father who is 71 inches tall. Show your work. So the residual for a son who is 69 inches tall, we need to find out, this is his actual. Let's make that clear. This is actual. Okay, his actual height is 69 inches, but we need to figure out how tall he was predicted to be based on his father's height. So we're trying to predict the son's height, and we're going to use the same exact formula as before, plus 0.84238. Dad's height is now 71 inches, so we fill that in. And then his height multiplied by this, and you add this, some buttons on the calculator later, 71.83 inches. So this is the son's predicted height. So this is son predicted. So we predicted his height to be this. In actuality, he is 69 inches tall. So here's his predicted, remember AP statistics. So his actual height is 69 inches. We're subtracting his predicted height of 71.83, and then calculator time. This gives us a residual of negative 2.83 inches. This means that this kid was 2.83 inches shorter than he was supposed to be according to the least squares regression line. So again, if you'd like to try number 3, you're welcome, or number 15, you're welcome to. It's pretty difficult. It involves the formulas from before about B equals R times the standard deviation of, I think it's y over the standard deviation of x, and then you have to use the buddy formula for a, which I don't even remember what that one is. So it's on the formula sheet for a reason, because they're hard to memorize. So if you want to give this a shot, you're more than welcome to. Otherwise, have a great day.